what I'm going to be talking about today is a little bit about robustness of machine learning and specifically about certification, right? How do you build neural networks or machine learning systems that come with provable guarantees? Let's see if this works. And so roughly, the field kind of operates this way. Initially, there is some task, like for instance, the ImageNet dataset, and there is a lot of interest in getting this accuracy going up, improving the accuracy, the standard accuracy on the test set. And so the community works a lot. We come up with new architectures, new ideas, new training schemes, and then the standard accuracy goes up, and then even surpassing human level performance sometimes. So this is what happened in one of the most famous data sets, the ImageNet dataset in Vision, which kind of even triggered a lot of the deep learning innovations. Okay, so what happens after, however, is that when these models start getting deployed in the real world and people start using them, all kinds of issues happen, which basically signify that just optimizing the standard accuracy is not enough. There is issues with bias, with fairness, with all kinds of robustness issues, and many others. And that's something we have experienced in some of the companies we started, also with government clients or other companies where, just trying to deploy these models in the real world is actually completely different than trying to optimize the test set accuracy. And so what this leads to is this desire, this interest to build machine learning models, whether it is standard classification type models, regression, or nowadays Gen AI models, LLMs, that come with certain kind of guarantees. There is also even the EUA Act, which, how many of you know about this? Like, do you guys follow this? Like, some of you follow, right? It's actually, we've been working quite a bit on this, so we'll be having a major announcements on this kind of a more technical interpretation and other things here. Anyway, so there is this need for guarantees, building machine learning systems that are safe, secure, and probably so, not just with respect to just testing or trying out some attacks. Okay, so this is the plan for today, what we want to do. I want to give you some intuitions behind how do you actually prove properties about machine learning models. And what are some of the fundamental intuitions, some of the fundamental challenges? Why is the problem hard? Okay. And these issues arise all the time. It doesn't matter if it's vision models, transformers, or text, or Gen AI models, LLMs, and so on. They're kind of very fundamental to reasoning about computation in general. Now, if you want to build models that are actually safe and secure, probably so, you also need to worry not just about certification and verification, you also need to worry about how do you actually regularize or how do you bias the models so that they actually can be proven with existing techniques. So the fact that something holds and is true doesn't mean that you can actually prove it with existing methods. So there is a whole slew of interesting optimization problems that arise when you start talking about proving things about machine learning. And then, if time remains, I will talk a little bit just about some of the ongoing projects in large language models and safety, security, attacks, defenses, and so on and so forth. Okay, so coming back to robustness, we're going to be using this as a running example for illustrating the techniques. It's not specific to robustness. Robustness is basically tied to individual fairness as well. Yeah? The mic? Oh, really? Or maybe I just step back here, or is this good, or? It's better, okay. Maybe you just move away from this. Okay. So we're just, yeah, so if you don't hear on the back, just let us know. Just let me know, and then I'll move even further, maybe over there. So, okay, so we're just going to be using robustness as just as an example of how do you actually what are these verification methods, certification, and so on. So there's been many, many attacks. It's a whole field, right? People like to break things. They like to break things, all kinds of things. And so this is some attacks on robustness. So you've seen some of this already. You have a bear, you have a panda bear picture, you had noise, and now the machine learning model misclassified something else. The middle one is kind of interesting. I don't know how many of you have seen it. So you have 3 different scenes. You add some stickers to the cameras. And then what happens is that the arrows, these 3 arrows, yellow, green, and red, are actually 3 different neural networks. And so for different pictures, the vision system actually tells you, to each of the different networks, tells each time to go to a different direction. So sometimes in the first picture, the red network is wrong. It tells you to go into the wall. And then in the second picture, the green one is wrong, and then the third one, the yellow one is wrong. So there is also regression tasks, like determining the angle, which way you should turn, and so on. And of course, physical attacks, where you just put stickers on stop signs, and then what happens is that the vision system thinks it's some speed sign. And there are many, many, many of those. There is thousands and thousands of papers on this kind of attacks. Nowadays, it's transferred to LLMs with prompt injections, jailbreaking, and all kinds of things of this sort, both in the discrete space and in the continuous space. Okay, so that's what's going on. But what we would like to do is to think about how we can actually prove that these kind of attacks or this kind of unstable situations or that this cannot happen, actually, and probably so. And so we need to understand why certification is an inherently hard problem, first of all. So why it's important is clear, but then why is it actually hard, before we look into the techniques. So imagine you have a situation here where you have an X-ray image X, and then you just feed it through the network, and then it gets classified to positive or negative. Okay, in this case, it's positive, binary classifier. And so what happens is, what you want to do is, you want to, if you stay in the robustness space or in the individual fairness space, what you want to do is to show that, when this image X is actually transformed in some way, either noise is added or it's rotated or some brightness is added to it or something. Maybe the machine has issues and it slightly perturbs the image. It could be a combination of these things. It could be basically a program that is run on this input and it transforms it in some way. And these transformations are in some range. So you have a rotation. The rotation is in, let's say, the angles between 0 and 2 degrees. You have brightness for the pixels, which are also in some range. Okay, so if you want to actually enumerate all these points, you will not be able to. Even for something like MNIST, you have more than 700 dimensions, so just 2 changes per pixel, it's 2 to the 780 or so. So this you cannot enumerate. Some people somehow think sometimes you can, but you cannot for anything decently sized. And so you cannot just enumerate perturbations and run and check what happens. And so what happens is, with certification, what you try to do is you try to summarize these perturbations that can happen to the input in some region, okay? And so what happens is, if you look at this yellow box there, and the points inside it, so each point is some perturbation to the input, according to the transformations. Some range in the transformations like translation, shearing, rotations, noise, and so on. And so certification methods summarize those in some formula phi, typically some symbolic shape of some kind, some convex shape. Doesn't have to be convex, but typically it's convex. And then what they do is they like to somehow take that shape, this yellow one, which can potentially contain an infinite number of points or unbounded number of points or bounded but large number of points, and to then propagate that shape through the network layers, so through the review layers, affine layers, or some other layers, whatever layers you have, and end up with something like, so look over here, so you're here, you push it through, let's not worry how, and then, but immediately, very quickly, we end up with these non-convex shapes over here, because these points get transformed as you go through. So there is exact methods which you can use to propagate this, like mixed integer linear solvers or quadratic solvers and so on, depending on what shape of the input is. But these are generally NP-complete, so they don't really scale. So if they did scale, you'd end up properly, you'd end up to push all these points, potentially infinite set of points through, and you'd end up over here, these yellow things. And these yellow ones are all inside the green region, so you'd be able to prove that any perturbation of the input actually is classifying to the same as the original input, like robustness. Individual fairness is the same property. Okay? So on one side, you cannot enumerate because it's at least exponential here. On the other side, if you use existing techniques state-of-the-art for certification, you actually cannot scale to big networks. So that's the problem. Okay, so it's important here whether the problem makes sense to you. Any questions here? Does this make sense, why the problem is hard? Okay. All right, so what's happening here is to address this problem, this fundamental problem, you need to somehow represent these sets of points that can possibly arise in the middle of the network, these yellow regions, in some kind of shape which you can manipulate efficiently. And that's called abstraction, some kind of relaxation, and that's where a lot of the game in certification is today. How do you actually represent these regions in a tractable way so that you can scale? Now the problem is, there is another problem when you do this. This is some convex shape here, some convex polyhedra, is that you introduce over-approximation, that there are points here that actually cannot happen under any perturbation of the original image subject to the transformations, and so you may end up with some region which is crossing the red boundary, and so you may end up not be able to prove the property because you are losing too much precision. So the question is, how do you scale while not losing precision? All right, and so that's what we're going to be looking at here a bit. Now there are several high-level points here so that you don't get the idea that these techniques are just for like robustness and vision and so on. So really the high-level idea here is how do you manipulate efficiently infinite sets, okay, symbolically. And these ideas we have found to be like immensely useful in all kinds of reasoning tasks. So these days we are working a lot on safe agents. So if you have agents, generative AI agents, you need to basically use the same techniques. Okay, so let's start getting a bit more technical so that you can get a bit the idea of what's going on. Let's instantiate it to some simple perturbations so that we can see the techniques of how do you actually do this. How do you reason automatically about infinite sets of points and be able to prove stuff? And then how do you actually incorporate this symbolic information during training? So this leads to different types of optimization problem than the standard machine learning problem. Okay, so let's first define the region. We are going to use, for our purposes in the lecture, simple regions. So here it's L infinity boxes. So in one dimension it's interval, 2 dimension is boxes, in more dimension is some form of hyperbox. So I hope everybody knows about norms. And so we have an image X, and then you put a bow around it of some kind. Here it's the hyperbox. And you want to reason about all the images around X within some epsilon distance according to the norm. Okay, so that's step 1. If you have fairness here, you would have an individual X, and in that region you would capture all the similar individuals, like those with similar salary or similar address or similar spendings or whatnot. So you can define these similarity regions, let's call them. Okay, so now the next step is, once you have these regions defined in some symbolic constraint of some sort, how do you actually propagate these things and how do you actually reason about them? And so here we have that region. So this is a bit, so going back, this is a L-infinity box. This is a bit different. This is just similar again. You have these pixels here, 785 pixels. Some are fixed already. Some have regions around them. So you have 0.975 plus some 0.025 times epsilon 1. Epsilon ranges between 0 and 1. So for some of the pixels, I have added noise, some interval noise. So this clearly you cannot enumerate because it's a continuous values here. So this corresponds essentially to a brightening attack, similar to the one that you saw with the stickers. Okay, so then what you want to do is you want to prove that no matter which point I select from this region, it always classifies to 8. So this basically says, this formula says for any input in the domain I which is inside the box, when I run that point through the network, it's going to satisfy the post condition, which is basically this is basically saying that it classifies to 8 in the logit space. Make sense? So very simple property, very simple pre-pose, very simple safety property. And so, as I mentioned already, you cannot just enumerate existing solvers, mixed integer linear solvers don't scale. SMT satisfiability modulo theory also doesn't scale. And so that's a problem. Okay, and so that's the idea. High level idea is that you take these shapes, and what you do is you do the following. Rather than taking a point and then executing the activations or the layers on that point, because you can't, in practice, enumerate, you have versions of these arrows. These are the layers here, like affine layer, review layer, or some other layer. And you have symbolic versions of these layers. So essentially what you have is that you have to make this layer operate no longer on concrete points. You have to make it operate on convex shapes. So you get a shape here after this layer, you push that through, and then you get to the end over here, and you get some shape here. I just made up some shape, some symbolic shape here. Okay? One thing you can notice here is that the dimensions here are actually correlated. So there is like epsilon 0, epsilon 1, and so on, so that it's not completely non-relational. So you can capture some non-box regions, let's say. Non-hyperrectangle regions here. Okay, and so once you get that shape here, what you do is you take that shape, the last one that you got before doing the softmax, and then you check your property somehow on that shape. So that shape can encode potentially again an infinite set of points here. Okay, so that's the high-level idea. And so there are two fundamental questions that you need to address when you're talking about certification. And the fundamental questions are, what are those shapes here so that they don't over-approximate too much? And what are those shapes so that when I push them through these arrows, through these activations, I can do so efficiently. And so the whole field of certification of machine learning tends to rotate around these two questions, basic questions. So let's look at now two basic convex relaxations. One is more basic to give the intuition, and one is more advanced. Both of these are very, very widely used. That's why I picked them, because they're used in training as well. It's kind of interesting how do you actually train with this. And they're also used in certification very heavily. So, but there are many, 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 many variants of subpolyhedra that people use on convexity that people use here. Okay, so let's look at the box. Some people call it interval-bound propagation. Some people call it intervals. It doesn't matter. So these are the effects of the layers of these operations like plus, minus, reu, multiplication by constant on the intervals. So you have an interval AB, A and B are real valued vectors. So if you have trouble with thinking about the vectors, just think that they are intervals or just scalars. So A is a scalar, B is a scalar, and then you're adding two intervals. You are negating an interval, and you're applying a reu to an interval. So these are the symbolic effects. So this is a symbolic region on the left side. Like, okay, so I have two symbolic regions, one AB, one CD, two hyperboxes. I have to add them. How do I add them? This is the new symbolic region on the right. Okay, so these are really simple. They're called abstract transformers. Unfortunate name clash with transformers, but really they're just summarizing the effects of the activations on the convex regions. So, does this make sense? So these are really simple, okay? And so you basically apply these things when you are analyzing those shapes that we summarize, and then you use these abstract transformers, they're called. Okay, so let's highlight a couple of points here that sometimes get lost when people are talking about certification. And also they're important for when we're discussing training. So look at this network here, right? It's X1, X2, X3, so they're just like four neurons. And we have some input region. Each pixel ranges, this one is between 0 and 0.3, this one is between 0.1, 0.4. So I guess this was centered around 0.15 initially, and then there is some 0.115 distance from the center. Okay, so the goal here is to prove that regardless where X1 and X2 are in this region, they actually classify to the same thing. So now what happens is, if you apply these transformers to that network, so here's the affine transform, X3 is equal to X1 plus X2, and X4 is equal to X1 minus X2, bias is 0, all right? What happens is, you get the bounds using box, or those bounds over here. Okay, so you can do the math. I think this is quite simple, and you would end up with these bounds over here. And these are the best bounds that you can actually get using this convex shape. Okay, so using the box, I couldn't have done better. But the problem is, there is a point which is this one, allowed by these bounds here that I have computed on X3 and X4. So X3 can be 0.7, and X4 can be minus 0.4, where it's actually not a feasible point. It cannot actually happen in this network if you look at the actual constraints. And you can check that. You can just take 0.7, plug it over here. You get 0.7 is X1 plus X2 minus 0.4, X1 minus X2, and do the math, and then you'll see that you'd end up with a value for X1 that actually is not feasible. And so even though for a given convex relaxation shape, you do the best that you can, you actually may have imprecision, which is kind of expected because that's the point of the relaxation, to lose precision so that you gain more efficiency when you're pushing it through. Does this point make sense? Okay. And so box loses precision, so keep that in mind when you're then later talking about training. So there is this point about optimality versus exactness. You may be optimal with respect to the particular convex relaxation, but you may not be optimal with respect to the exact thing that you get. Okay, but this doesn't mean that the fact that you are not optimal, you'll not be able, the fact that you're not exact, you will not be able to verify the property. So if you take slightly more complex network, you can apply the box transforms, apply through the rail you here, go to the end, go to the output layer here, O0 and O1, and check that you can actually prove that O1 is always greater than O2, right? Do you see why the case? O0 is always greater than O1. Do you see why that's the case? Because the upper bound in the interval for O1 is less than the lower bound for the interval for O0. Okay. And so the fact that something is not optimal or it's not exact doesn't mean that you cannot prove things. Oftentimes you can prove a lot. And when you're training, what you're trying to do, these networks for certification, you're trying to bias those weights. Here you see it's 1 and bias and so on. You're trying to tweak those weights so that you lose minimal amount of precision. So neural networks generally tend to be fairly simple, loop-free, mostly differentiable programs. So you can learn the parameters of the network so that a particular symbolic propagation or convex relaxation behaves more tighter. That's what training would do. Okay, of course, if you widen the input interval a little bit, now it becomes 0, 0.6, 0.1 to 0.7, box is too imprecise to prove the property. Okay? Even though this property actually holds here. So for this network, it is true that no matter where you are in this interval here, you actually can, it is true that O0 is always greater than O1, you just cannot prove it. So the fact something is true and you cannot prove it, it's kind of useless. That's an issue. One thing that I should mention here for why we like automated reasoning like this for when you're doing machine learning tasks is that, and now it also with the agents is becoming very apparent, safety, because you actually can reason about a computation without actually running it. So you can reason about a computation without actually running it. I'm never enumerating anything. So that's important. Okay, so we saw a little bit the problem with this very simple relaxation. And so one of the issues with this relaxation is that it was losing precision on the affine transform. So if you have an affine transform here, it's actually losing precision as well. It's not exact. And so let's look at another one that people actually use for it's a bit more advanced, that they use for certification these days. And I should say that these relaxations, they actually initially people thought that they scale to like very small networks, but nowadays, especially with certified training, they tend to scale more and more. So it's actually quite, I would say, mid-sized networks they can handle. And so what happens with this convex relaxation here, it's again a restriction of convex polyhedra. And so here's the situation. What happens is that at every neuron, xi, you are keeping 4 constraints. So 2 of these constraints are just like before, the lower and upper bounds for that neuron, just like the box. But 2 of the other ones are relational constraints. So here, xi is greater than or equal to ai, and ai is some linear expression over potentially prior neurons. And same thing happens for the lower and the upper bound around xi. Okay. And so this restriction of general convex polyhedra to contain only conjunctions of these 4 shapes tends to, gives much better asymptotic complexity than the general exponential complexity for polyhedra. And so it tends to scale quite well, and it's quite precise in practice. So that's the game in certification. You're trying to figure out restrictions of the general shape so that you can get better asymptotic complexity transformers so that without losing too much precision. If you have, transformer networks, let's say, you'd need to provide ways for these activations and transforms to transform those constraints here. Once you do that, you can basically handle any computation, any network. So let's see what these abstract transformers are here, because they're a bit more complicated, so that you get a sense of this. So this was the case with the box relaxation. You have this simple network. This is the input region here. Could be that you added some noise, could be brightness, could be that it captures rotations, could be individual fairness, it doesn't matter. It captures some convex region, and you're trying to prove that everything in this convex region classifies to the same point, same label. So here the property holds, but box cannot prove it. So now we need to see how deep poly would actually prove it. So let's start like this. You have the shape over here, and you take that input shape, and these are the constraints according to the deep poly allowed constraints. So you have the lower and upper bound associated with the neuron, and initially it's the same as for the rest of for the other 2 lower and upper bound linear constraints. Okay. And then you push it through. You take these shapes here, this and this form the box, and you push it through applying the affine transform. So if you apply the affine transform here, you'd end up with like x3 is equal to x1 plus x2, which you represent as 2 inequality constraints. So that looks fairly straightforward here, right? No surprises. Now comes a bit the tricky part here with the ReLU, these piecewise linear functions, and what to do. What should we do here? And so the situation is as follows. You have a ReLU activation coming on some neuron xi. Okay, you get the neuron xj. And then you have these lower and upper bounds. So one question is, why do I need these concrete lower and upper bounds when I have the linear expressions lower and upper bounds? And we'll see in a second why. Because you use them for the ReLU. So here is how the transformer, or how you would propagate the convex shape for the ReLU using the deep poly convex relaxation. So first you check whether on the input neuron the upper bound is less than or equal to 0. In which case you know that this value is less than or equal to 0. In that case, you basically, for the new neuron, the bounds are basically 0. Because that's what the ReLU does. So non-crossing ReLU. Then you check the other side, whether the lower bound for the input neuron is greater than or equal to 0. And if the lower bound is greater than or equal to 0, then you're essentially carrying over the constraints for xj from xi, and that's what this says. All right. Now the interesting bit here is when the lower bound is less than 0 and the upper bound is greater than 0, so it is crossing. The ReLU, the input, the values for xi are crossing. Okay. So here is one relaxation that one approach to a ReLU relaxation using deep poly. So you have for your input neuron the lower and upper bound over here. Okay, this is the lower and upper bound, and it's crossing. Now you have to approximate this function, the green one, the ReLU function. If you just keep the constraints, the green lines, then you'd very quickly get intractable in terms of computational complexity. So you got to approximate it somehow. So how do you approximate it using the shape that's allowed by deep poly, where you have one lower and upper bound concrete and one lower and upper bound symbolic. And so what you do here is you say, with this particular relaxation, you say, well, I have this line over here. This is the line y greater than 0. So certainly I got to go above in that plane. I have this line over here. I can calculate the slope from the values Lx and Ux. And I can calculate this line here. So this is the line over here. Y is the slope times x minus Lx. You can check this. That's fairly direct. Y, what's the slope and what's the distance here? And so you have this line over here. You have this line over there. And so your shape for the output neuron would then be bounded by these two lines over here. So it would be y is less than or equal to going downwards from this plane and then going upwards from the 0 plane. Does this make sense? Or no? So you're trying to calculate the lines and then bound this shape somehow. Of course, this introduces a lot of infeasible points. All these points here are basically infeasible. Hopefully, downstream, some of these points will disappear via other transformations. There's another relaxation. You can also go down this way. By not just going this way, you can also approximate the line this way with these two constraints, because we are limited by the number of constraints we can use. All right. So you can, this line is the same, and then you need this line, which is the line y equal to x. And so you just take the plane from here. Okay, so these are two relaxations that are commonly used, very commonly used. One thing, of course, you'll notice is that you can vary the slope of the approximation. We don't have time to go over this, but the slope of the approximation can vary. So you can take these points here, vertical line around Ux, and you can go this way. So these are the extreme points. You go this way, but you can slightly go up on this line, slightly go down on the right side, and then you end up with slightly different shape. So here we have fixed the slopes with these approximations. You can actually parameterize the slope, and then you can do optimization on this parameter in order to find slopes that are actually good for verification. One thing that you should notice here is, and that's important for training, is that here in this approximation, you have one region, you have one area. Here you have another area. And so when you're actually verifying, what people tend to do, they calculate both, and then they pick the one with the smaller area. Of course, these are non-comparable shapes. So it could be the one with the smaller area actually behaves worse down the line. But it's a heuristic. But this kind of selection during certification is fine when you're doing certification. This kind of selection on a forward pass when you're doing training is actually problematic because it introduces discontinuities. So this actually leads to some fundamental problems around certified training that took the community a while to, yeah? Yeah?
Why do you need to compute the points if x is smaller than 0? Because the redo should be 0. So if you get rid of them in those computations?
Well, so the situation is that you have to, there is relational information which is captured by, so you have linear constraints, and these linear constraints are in terms of expressions, and they are actually related. So it could be the case that you have two expressions. So if you actually cut the line a bit, you may actually lose soundness on other values. So it's a soundness question. We can, if there is a board here, we can probably give you an example. All right. So that's this line. You actually need to capture it here for soundness reasons. So it's a bit more involved, like why you need to actually keep this line over here. Okay. So, but as far as training goes, when you're trying to bias a network and regularize it so that it is provable with a certain method, then you need to be very aware of this kind of discontinuities. So the community for a long time wasn't, and then it got into a lot of problems. Okay, so let's continue with the first relaxation just so that you get the idea. So if you apply this relaxation, just like we saw before, the first one, you would end up with these constraints over here. You can check them. So you get some constraints, some linear constraints. Okay, so you get them. You get the constraints. And now you have the next step, which is the, over here, this is the, after the review, and now you still have an affine layer to worry about. So what you can do is, again, you apply the affine layer. What you have with the affine layer, x7 is equal to x5 plus x6. You can express this with the constraints. But then you have a problem with the lower and upper bound over here, the concrete lower and upper bound. Remember that the concrete lower and upper bounds are actually used for the review. So we gotta get them back. And so if you actually take this, you say, I'm going to compute the upper bound, let's say, or the lower bound for this neuron, you can just do the interval arithmetic here, and then you would end up with this value here, because we have x7 is less than x5 plus x6. Okay, what is the upper bound for x5? It is u2. What is the upper bound for x6? It is 2. So you would end up with 4. 2 plus 2, 4, minus 0.5, 3.5, so you end up over here. So that would be your upper bound. Make sense? Okay? But the problem is that this upper bound is actually not tight as it could be. And so if you just apply on these constraints coming out of the review, you apply the normal interval approximation, then it actually gets imprecise bounds. And so you want to refine those bounds, and you do this by something called back substitution. So rather than getting those bounds here, which we will later use for the review approximation, as we saw, we want to get tighter bounds here. And we get tighter bounds by starting to substitute backwards these constraints earlier from the ones we already have. So if you start doing this, you have something like x5. So let's take x5. You take the upper bound for x5 using the constraint over here, the 0.5 times x3 plus 1. For x6 is going to be 0.5 times x4 plus 1. So if you substitute it, you're going to get this. and you can substitute back to the beginning or to some point where you have good lower and upper bounds. Does this make sense? So you can substitute back to capture some of this relational information. And so this back substitution, this is what it does. And if you actually take this example and back substitute to the beginning, you'd end up with an upper bound of 2.5 and not 3.5. You're trying to recover some of the lost relationality information that you're losing on the forward pass. And so this back substitution, you can back substitute to the beginning, you can back substitute 1 layer, 2 layers, 3 layers, up to some heuristic where you think you're going to get good bounds. Yeah, let's check the time. I have some time. Okay, so this is how this, so if you do this back substitution, you'd end up with like the upper bound 2.5 and not 3.5, which is kind of nice. It's a much tighter bound that you can use later for the REU. And based on that bound, you'd get tighter REU approximation and so on and so forth. Okay, so that's kind of the high-level idea about this convex approximations. If you get to the end, like you have this substitution here, just to mention, it's important. You have this expression here, you're trying to compute the upper bound, you substitute back to the beginning for the constraints, you end up with like 2.5. Okay. And here we are able to do it, we were dealing with a very simple box here, or some hyperbox, so it's easy to substitute. If your input region is more complex, it's some other norm, some L2 norm, or some other region, and you're substituting then just simple substitution just to the beginning directly will not work, and you need something called the Holder inequality to handle arbitrary norm input regions. We're not going to go into it here, it's just for you to know that you can apply these convex relaxations, not just with L infinity norms and other kinds of, you can apply them with other norms. Okay, so if you actually do deep poly on this, you'd end up with the following constraints here. If you're doing an exercise in a course, you have to really like check these coefficients here because they look suspicious, how you get them. It's actually, to analyze this network, actually we had to switch from one relaxation, REU1, to the other one that I showed you. But at the end, anyway, for the output neurons here, you end up with the following constraints. But my goal was, you know, this is an over-approximation of potentially infinite set of points that are captured in the blue region at the end. And my goal is actually, how can I use this information? So I can use this information in many ways. One is to prove stuff. One is that people use this kind of symbolic reasoning in, you know, things like models for code, language models for code, where you need to extract features. So this actually, if you look at here, these are actually feature extractors as well. I may not care about proving anything. I may just care about some properties of the computation. For our example, we're using these extractions for proofs. So if you go back to the end, we are just trying to prove that over here, the values that you get here for x11, they're always greater than the values that you get for x12. So I want to prove this constraint holds. x11 is greater than x12. And once again, you have that issue to where if you take those constraints over here for x11 and for x12 that you get from the poly, okay, and you just do interval box arithmetic on this by just using these bounds over here, the lower and upper bound, you will fail to prove the property. You can do the exercise by just plugging the values over here into the constraint over there. Okay, so you need the lower bound for x11, and because you have a minus coefficient, of course, you need the upper bound for x12, and so you end up with 0.5 minus 2, minus 1.5 greater than 0. That's not going to work. And so again, you do back substitution up to some layer, and then maybe to the beginning, maybe if you're lucky, just a couple of layers back, and then you're able to prove this constraint, because the lower bound for this expression would be 0.5, and then that's enough to prove the property. So that's how like automated convex propagation and convexity works for proving stuff for neural nets. Going back over here, if you have a new architecture, all you need to do is to define the abstract transformers for the particular activations, and then you can use it for any network that uses these activations. Okay. So that was the summary of the deep poly. It actually has many names. Deep poly is the one we used. The one from Eric Wong and Zico Coulter at CMU, it was using, and Huan Zhang, they were using the name Crown. Others are using different names. It doesn't really matter. These are all restrictions of convex polyhedra to get better asymptotic complexity than the general polyhedra while keeping good precision. So this is the complexity of deep poly and the complexity for box, so it's a bit higher, but certainly not exponential. Okay. So I hope this gives you a bit of an idea how to apply these techniques. There is libraries with this, you can use them, you can change them. You can apply this to text models by just looking at the embeddings, not just at the discrete space. So people have applied it to all kinds of things, reinforcement learning, vision models, robotics, code models, and so on. Yeah? Yeah. Exactly, yes. That's a very good point. We'll discuss it in a second, actually. So one of the limitations of these methods is that when you have deep networks, the imprecision accumulates. And when the imprecision accumulates, you may not be able to prove much. People have actually done architecture search with respect to this certified training to try to get it to prove more. It's actually not much work in that space. So how many people know about the lottery ticket here? A few people know about the lottery ticket of Mike. So they've tried also to use lottery tickets for this kind of, going beyond accuracy. So there are certainly limitations. Yeah. Yeah.
You have some special interactions, you have zero intersections in your input. And you can make one convex and the other.
Yeah.
And have the both.
Yeah.
Because here there's an interlude that does something else.
Yeah. You can propagate multiple shapes, that's fine. It doesn't have to be a single shape. If you don't have any interaction, you don't have to combine them. You can just keep them separate and propagate them separately. This happens, some disjunctions of shapes.
Yes.
Yeah. This happens. The problem is, if you have too many disjunctions in the middle of the network, it can explode, right, exponentially. But people do this. They keep sets of shapes so that they don't merge too much. Yeah, that happens.
Is there any research if you have some shapes with holes?
With what, sorry?
If you have four-dimensional shapes that have holes that are not convex, can you make some sort of?
Yes, there is also transformers for non-convexity. It doesn't scale much, but there is. Of course, like when you do, so we'll talk a bit about it. So when you have certification like that, that's just the baseline. You typically combine this with some kind of mixed integer linear solvers. Okay, linear solvers, typically some restrictions on like Lagrange multipliers to capture splitting. And so you have branching there, and when you have branching, you have non-convex. And then you learn how to branch and so on and so forth. So you typically slap some Lagrange multiplier type linear solver together with branch and bound, together with deep poly to do the full-blown verification. And then you have non-convexity everywhere. You have lots of splitting and so on and so forth. Okay. So let me give you something which is, so one thing you need to understand, that's how we picked it here, is why do we like symbolic reasoning? Because you learn to manipulate multiple infinite sets at once, and then we use this in all kinds of many different applications. Now, these are completely separate areas of research. Typically, people who work on certification don't work so much on training. And so this led to actually some problems. So in the courses, we teach them together, but in the research, sometimes they're separated. So one of the problems here is that if you just take a network, whatever the network is, and you take the most advanced methods like this combined with some Lagrange multipliers with mixed integer linear solvers, and you try to prove stuff, you're not going to prove much because the property simply doesn't hold. The network is not robust. The model is not robust, okay? And so what happens is that you need to actually find a way to bias the network to be robust, the model to be robust. Not just for the property to hold, but for the property to provably hold. And so that's the question. How can you actually combine training and certification? So here's the high-level idea that summarizes the whole area, I think, of large amounts of certified training. So the idea is like this. You have a shape here, some convex shapes, maybe sets of shapes. And what you do is that you push that thing through using deep poly, box, or whatever technique you want. It doesn't matter. You get some shape at the end. And then what you want to do is to change the weights of the network so that you actually get something which doesn't lose as much precision. And so what happens is, you go to the output shape, and this is how the optimization problem works. Here's your region, push it through, get here, deep poly or whatever. And now so this notation here, NS sharp, which just means the abstract effect of Sx, is just the shape here. This shape is this thing here. And then what you say is like, go and find the point here, which maximizes the loss, which leads to the worst behavior of the loss. You find the worst behavior of the loss, and then you change the weights to mitigate that bad behavior of the loss. This kind of, think of it this way, I have a computation, I'm trying to change the parameters of the computation so that when I analyze it, the shapes that I get smaller, the over approximation gets smaller. Does this make sense intuitively? Yeah?
The worst loss always on the vertex.
Doesn't have to be. Can be somewhere else. Depends on the loss, depends on the shape. That's what happens. Okay, so side by side, so that you get the idea more technically. This is the standard adversarial training, PGD training, that is classic. Now, in LLMs as well, when you're trying to optimize the continuous representations of the prompts, people do this. The adversarial defense, so-called. So what this thing does is, I on purpose put them side by side. Where is this thing here? Does it work? Don't know. This is like advanced button. Very good. So what happens is that on the left, this is the adversarial training. And so what it does is it essentially has this min-max problem where the inner problem, the max, here takes a point in the input space in the adversarial region. And then it tries to find the worst case behavior of the loss on that region. And then it minimizes the weights so that the worst case behavior is reduced. So that's how it works. For the certified training, it's not the point in the input region, it's the point in the output region that you get from the convex shape. So here what it does is it takes a point at the end of the analysis of the propagation, like this point Z, and then it tries to maximize the worst case behavior of the loss. So one works in the beginning, and one works at the end. It works at the end because it tries to mitigate the effect of the approximation induced by the convex propagation. So these are the two extreme ends. So of course, when you see two extreme ends, you're probably thinking what's in the middle, right? So if you just ask this question, you'd end up with like very interesting schemes of combining both. And so one of the problems here is with certified training is that, and we realized it only a couple of years ago in the whole community, is that here you are no longer backpropagating through the normal activations, affine layers or whatnot. You are backpropagating through the symbolic versions of these layers, these abstract transformers, which is much more complicated. So this is essentially, you have symbolic computation going forward, you're backpropagating from this. It's a hard problem. And so this formulation of the certified defense that people use to this day, and many people use it, actually it is a hard problem. So we've been trying to find other optimization problems. So here's a couple of notes. Cheaper relaxation like box than deep poly. So box is much less precise than deep poly. The deeper the network is, as he mentioned, the more precision you lose. Meaning you're training with respect to more infeasible points. So you're training a network to be provable with respect to infeasible stuff. Okay. Deeper networks, more infeasibility, more infeasible points because of approximation. So the fundamental goal here with certified training is to actually reduce the number of infeasible points in the forward pass, and then use more precise relaxations, and then don't lose so much precision when you're picking those points over here. But here is a problem. So what do you do when people say this? They say, well, just use more precise relaxations. What's the problem? Just use deep poly, not box. And that should solve the problem. More precise, less over approximation. No problem. And so that's what we did, and the community did for a while. We had students, very smart students, like working in this way. And you just run, and you pick more precise relaxation, and you get worse results. So more precise relaxation lead to worse results. Worse meaning worse accuracy for the resulting network and worse probability. So everything is worse. So this makes no sense. Like from a verification perspective, this makes no sense. You're basically picking something more precise, and then you're getting worse final results. So why is this happening? Any ideas? Accuracy, probability, everything. So from a verification perspective, if you're coming from the verification community, this makes no sense. And so people there were really confused, and people who are working in machine learning also are confused. Why is this going on? Okay, so there is a paradox. So this is a paradox here, you can see it. So tightness measures how tight it is. So the higher the number, the more tight. And 35% means how probable things are. So what it turns out is that the very simple box that we looked at actually is the least tight, but leads to more provable stuff and more accuracy. And the more tight it gets, the worse the results, and by a large factor. So the community, I think, was stuck for 2 years for sure. Throwing more GPUs, more compute. I don't want to say for what some people did, because it would be embarrassing how much compute they tried to solve this. They just couldn't believe it. They're like, no, I don't accept this. I'm not accepting this. I'm putting more precise relaxations, and I'm expecting better results. So I'm just going to run the GPUs until I get better. I don't care. So here's a paper we did, I think, after we hit our head so many times. The lead author is actually Nikola Jovanovic. He's from Serbia, one of the PhD students in the lab at ETH. And so what happens is that why it happens is that the more complex relaxations essentially lead to worse, harder optimization problems. They have more parameters. This deep poly has more parameters than the box. And so with a very small number of parameters in the network, you need to control many more other parameters. So we studied this problem and continuity and sensitivity and so on, how the convex relaxations affect the optimization problem. So that's what happens. These things tend to induce different optimization problems. I really encourage you to read this paper, because once it came out, it changed like the direction of how people were working on this. Okay, so I hope that this gives you a bit of an idea about certification, convexity, that there is nice problems, optimization problems. The problem is still very much open. Coming up with simpler optimization problems, combining certified training, adversarial accuracy. We're hitting the same problems now with the generative models. It's basically, you cannot escape this somehow if you want to prove stuff. So it's a very interesting space, I think. You have, there's been 30, 40 years of research on, let me go back here, on forward propagation in automated reasoning. But if you are actually doing, you know, projected gradient descent or certified training or anything like that for certified defenses, you probably already have guessed that you need to project onto these shapes. Because when you're searching for violations, here, how do you actually get these points? You need to project. But projections onto different restricted kinds of convex polyhedra are actually not studied almost at all. So there's very little work on this. So if I tell you you have a deep poly, what is the complexity of the projection operator? We don't know. Like, it's not linear. What is the best one? So without actually advancements in advancing projection, like better algorithms for projections, efficient ones, I mean, you actually have trouble with this problem. Okay. So I encourage you to read this paper. It's actually an interesting paper and conceptual paper. And of course, because it's like this, we had trouble getting it into ICML and EURIPS because it had, I think, a lot of insights that didn't exactly have to do with state-of-the-art numbers. But it's, I think, very interesting. Many people, it switched the area a bit. Okay, so that's what I wanted to tell you a little bit about certification. These methods have advanced quite a lot. Basically now, essentially, it comes down to optimization with convex relaxations, some kind. So they scale to, I would say, few million size networks. And people use them in different domains. Okay, so I wanted to tell you a little bit about some of the ongoing topics that we work on. So trustworthy ML is a huge area nowadays with LLMs. In that space, we are actually still a bit behind. We're still attacking mostly. We are not, we're not still at the point where we can, we don't understand like the limitations and so on. So we're working a lot on that. Like, so this is a recent work we did on. I think it's in one of the workshops. It's submitted also oral at one of the workshops next week at Vienna in ICML. So the idea here is that you actually, when you quantize networks, large language models, actually you can exploit this and generate attacks with the quantized models. So people upload models everywhere, lots of public models, and you can upload a model such that when the model is quantized, it becomes malicious, even though the original model is not. So that's actually quite a nasty attack. Another one that we did is, as you know, large language models, they're very large correlation databases. So this is a new kind of attack which can infer private information by just leveraging correlation. So I find information about us, about you, which is not in the training data. So this was actually profiled by the White House competition. So it's also a very nasty attack. Which is hard to defend against, and we also did this for vision models. I think it was an oral or spotlight at ICLR, I don't remember. Recently, Jovanovic, who was on the Paradox paper, been working a lot on watermark stealing, so we have a lot of works on stealing watermarks from models. Another thing that has changed, I think, the area of code in general is the critical vulnerability database. I don't know how many of you know this. So there is CVE databases where people post critical exploits. And so we started this project, which is not really research, but more like gathering a lot of these prompt attacks and so on and so forth in one place so that people can actually figure out what are these vulnerabilities and defend against them. We're doing a lot of work on hallucinations, detecting hallucinations, fixing, and on secure code generation. It's one of the major use cases of the language models. And how do you actually generate provably secure code? And you're back to the same problems that we looked at today. One thing that's not here is stuff around agents. I guess many of you know about agents and safety of agents and proving things. The agent needs to run stuff, like a file system operations and so immediately when you have to run stuff, if you have ways to extract features from the computation without actually running it, like the way I showed you, you would actually be able to get provable agents, and it's a direction we're looking at. Okay, so that's the idea. I hope you got a little bit of an intuition about the hard problems, how to prove properties with convex relaxations. These are building blocks for all the certification methods. today. The certified training, or how do you bias networks so that, and models so that you actually can verify stuff, is leading to all kinds of interesting optimization problems that have not been studied much. These are, I think, fundamental challenges. And there is tons of work happening, I think, in the LLM space. And next week in Vienna, if you are there, come over and we can chat more about this. What else? I actually had a slide about, because many people ask me about Insight. I have a slide, and I'm very happy to see that there is an institute also here in Serbia, so check it out. So we've been running Insight with, it's created with ETH EPFL. It started 2 years ago. We're very happy to host you there. Come over, give talks at Insight. It's in this building. So we're working on a lot of these topics there: LLM, security, safety, a lot on foundational models. You know, things like that that are on the slide. So foundational models for robotics, language models, space data, things like that. So we have lots of visitors, PhD students. So if any of you are interested, if you're coming for Sofia, or interested generally internships and so on, just come over and ping me, and then we can arrange it. Okay, so that's it. Thank you very much, and yeah, see you. Is it right on time, or?
Questions?
Yeah.
So regarding the grouping techniques here,
Yeah.
is there anything else used besides like convex optimization, or are there any other ways that you can improve the robustness of the system?
Yeah, so that's what I mentioned. Like nowadays, you know, we have a whole course on these things at ETH, right? And so the ingredient of convex relaxations is just extracting those constraints. Those constraints get combined with Lagrange-based optimization, because deals with constraints, and it gets combined with, and also you can run a GPU. And this gets combined with branching, various branching things. So yeah, definitely nowadays verification is reduced optimization using these constraints as ingredients. There is also things like multi-neuron constraints, when I looked at single neurons, convex shapes over multiple neurons, and stuff like this. So it's a very, I think it's a very, so it actually, what we've observed at ETH and now at Insight is that people who actually do research in this first, they really are able to do different kind of research later in completely different areas, like differential privacy or LLMs and so on, because the techniques somehow like are very fundamental, and they kind of appear again and again in different weird contexts. That's what it is. Yeah. Yeah.
So regarding real-world applications,
Yeah.
so you can certify your model,
Yeah.
your data. So one thing is like the size of the box, right? Yes, you might have that. But what about the data? Like what's not in your data? How do you certify that you see?
Well, that's a different problem, right? So what we showed here and with the robustness, essentially it's being robust to distribution shifts, because the box captures something which is you haven't seen in the data with some shift, right? If you want to go to things that are outside the data completely, then I think there is a problem to start with. Also happens with LLMs on where is the model not behaving at all? So there's holes in the model for certain data which it doesn't work well. So finding out those things, there are startups and companies that are doing literally this, trying to figure out where it doesn't behave. And then via augmentations or whatever, add this kind of data. But another thing that's interesting, I think, about the relaxations is, of course, we showed it on robustness, but what we have found out, especially in some of the applications in the US, they use them like air flight controllers. They use them with other safety properties. They don't start with boxes. They literally say the plane cannot turn, or like it should be up to some angle, and the ground should be that much. So they have these constraints. They write them down. So yeah, robustness is a good example to illustrate techniques, but they're applicable to any kind of safety property. If you have, how many of you know like deep equilibrium models? Some of you know the deep equilibrium model. So these are basically things that like monotone deep equilibrium model. So these are things where you take an input and then you run kind of a fixed point. So you have a single layer kind of computation and you run it to a fixed point, and based on that you make predictions. And so what would happen here is that you need to deal now with unbounded unrolling computation. So there's very little work on this. How do you reach a fixed point? I mean, here it's easy, it's loop free. It's bounded number of layers, but it doesn't have to be. And then you'd end up with more challenges. But it's a good question. We can talk at length about this because we've built language models that are used countrywide. So we have millions of real world data, and we're actually trying to figure out where the model doesn't work. It's very tricky to figure this out. And then certify. Okay? Anybody else? Yeah.
So how do you come up with constraints for problems where there's, for example, some like particular structure in the data that you're expecting to see? So like, is there like an automated way to come up with, let's say, the right constraints to capture that?
Not really. There is not. So the question is, how can you come up with the inputs with the specification, basically, right? Like with input constraints.
Like,
Yeah.
for example, when you get an example of this image,
Yeah.
let's say the stop sign. So you're like expecting that maybe on the center of the image there will be some sort of, there will be a variation because someone put a sticker. So if you're expecting this to be, let's say, more, well, in the center rather than somewhere on the sides, if you have maybe a different model that would like segment the sign, right? So like, is there a particular way to do that?
So for this kind of robustness type of tasks where you have regions and you want to be robust to any change in that region, right? You'd put the regions and then you'd say that, or you can search over the space and then just search over these regions. What happens is, there is something we didn't talk about. I don't want to go back to the first slide. It's when you have transformations, each transformation is a function with certain parameters, right? And when you combine these things, first rotation, then, I don't know, shearing, then contrast, blah, 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 right? It's essentially writing a program. And then what happens is, if you have data, you can actually estimate the likelihood of the parameter. So it's much more likely that you care to be robust to small changes of the angle then I care to be robust against like 15 degrees because, I don't know, then the driver would see that there is something wrong. And so essentially what ends up here is you end up with distributions over the parameters. You essentially end up with a probabilistic program. And so now you're not pushing convex shapes through, you're actually pushing distributions through. So that's why I said that this area merges with a lot of interesting areas, because you have probabilistic programs, you can estimate the density, and then you can push the density through the network, not the shape. So think of the shape, it has density there. So that's a very interesting problem that people have started looking at, because it's not uniformly that you care about all the points, right? So that's also a good question, yeah. All right, I'll be here for another half an hour, I think, 40 minutes. Happy to chat after the DeepMind talk, and then in Vienna if you are coming there. So again, thank you very much, and